So I'd like to thank Saeed for posting an interesting article that I'm about halfway done it. It's a long one, which is nice. Well, finally, some interesting information. And I'm just at this point now where this is awesome. Something called the O factor. You know, I feel like one of the things that we haven't had a lot of access to, and I was talking to a student about this the other day, is good statistics on, you know, what's happening with COVID and infection rate. I feel like we're not really given a lot of good data to make decisions based off of. And I like this one here. This is a good statistic. So the total vaccine doses per week divided by the number of new infections per week. So again, as a stats teacher, I love any sort of new index. And I haven't heard that one before. So thanks for bringing that to my attention. Yeah, I think that's funny, the O factor. I like it. This equals the number of vaccines. I guess it doesn't matter what the timeline is. It could be per day, it could be per year, it could be per month. They're doing per week. But again, you could say it's basically the number of vaccines over number of infections. I guess they're saying new vaccines over new infections per unit time. But I like it. So right, as your vaccines increase or as your infections decrease, so there's two ways to get this number up, right? A big O factor is good. And there's two ways to do it, right? Either you increase your vaccines or you decrease your infections. It doesn't really matter which way you do it. Ideally, you would do both. So if they said alpha 0.05, graph it, that means that we're talking about this. In other words, 5% of the values are higher. So if you see something that says Z 0.05, that's what this indicates, is a Z score that separates the top 5% from the bottom 95. And of course, you have to kind of make a little, if you're going to look it up on your formula sheet, you'd have to look up 0.95. Because again, that's how this chart is given. So that's why I'm bringing it up. It's an added level of complexity in a complicated world. It's going to be a positive score because it's on the right side of the mean. And then you would find 0.95, which is between two values. So again, you essentially just kind of practice looking at this thing until you see that, you know, one's a little too big, one's a little too small. And then you can hunt down your first two digits here, 1.6. And then you can hunt down your last digit. Let's split these in half. So so in other words, I would say a Z score of 0.05. Sorry, Z score critical at 0.05 is 1.645. And so you really want to go through and identify anything that could be important, right? So like this number here, 70, this looks important. Normal, that's good. That means we'll use Z scores, the mean, and then standard deviation. And then obviously find the percentage of women who satisfy that height requirement. So you have to be, again, maybe at least would be important here. But, step one again is like and we're going to start building up the scientific process, right? The scientific process is the goal of this course. And by the time we get to the end of it, you should be able to set up a 6-step. Like, you remember when you were even just in junior high or high school and you had to do a science lab report, right? There was, you had to do a background, you had to identify the problem. And we'll be doing that with lab number 4, where we're figuring out the mass of Earth with a pendulum and conducting an experiment. But the scientific method has distinct processes. And the first step is always, what do we know, right? What's the background? What, in other words, what do we know? What's given? What do we know? Well, what I want you to do, and as they mentioned there, put what you do know onto the graph. So we know that the mean, which is here, so the average height is 63.8 inches, and we know the standard deviation. And we want to know the question, basically, right? What are they asking? They're asking, what's the probability actually the question is, what's the probability that a given person is greater than 70? Right? That's really the question. And, you can write, again, where would that be on this graph? It doesn't have to be to scale, but just put it somewhere to show me that, you know that you're going to have to calculate this area. Right? That's what we need to figure out. And if you don't write that down, a lot of people get it wrong. I was mentioning that in class, I think, yesterday, is that, you can use Excel, you can use a handwritten, the Z-score chart. I recommend doing both. Because, again, a lot of people will get this wrong just by using Excel, because you're going to get the wrong area. But I want you to make me at least something like this. You can do this in Excel as well, and I'll show you guys how to do that. But the point I'm trying to make is that this is the background, okay? And even if you did everything else wrong, if you forget your calculator at home, I'll give you, basically half the marks just for writing this down. Everything here. Like, this is worth a couple of marks in my eyes, right? Because you know what the symbols, you got the graph, and you know the problem. Right? And then, the next step in a scientific point of view is, what's your method? Or your hypothesis. What's your method? Well, my method is that because these are normally distributed, let's standardize it. Let's create a Z-score. Right? So let's do that. Let's get a Z-score. So Z, write down your formula, before you plug anything in. That way you can also get marks if it's wrong, right? And then you put everything in there. You can just use Excel as a calculator. So you have a Z-score now, right? And that's great. 2.3846. 2.3846. Okay, great. So we have a Z-score. And then we just, now that's the only new step, right? So now you just do what we did last class, right? So once you have your Z-score, you figure out, you do another calculation, let's say. So let's calculate the probability. In other words, let's solve the problem. Right? If I know that, what is the probability of getting a Z-score that is greater or equal to this? Let's round it because our chart only works to 2 digits, 2 decimals. So let's round to 2 decimals, which would, because that's a 4 and we're rounding to 2 decimals. Let's go 2.38, and we'll see if it's different than what I get on Excel in a second. But we got to go 1 minus the probability, and it's less than 2.38. Because again, that's what our chart gives us, right? It's it gives us everything to the left, right? We're going to get, again, this is why I want you to draw that down, because when you look up 2.38, you're going to get this value. So then you use your magical chart. Pick your first 2 numbers. And then after practice, you start realizing this is the 9 value, right? Here's the 8 value. So 0.9913. So again, this is kind of cool because if you're a city planner, or again, if you're a project manager, like this, what a great example. So it's true that light bulbs do have an average life, right? Like a light bulb, anybody that buys a light bulb, right? You'll know that there's an average lifespan. They tell you, but they don't tell you the standard deviation because nobody knows what that is except for you guys and other scientists. But they'll say average lifespan of this, and then this is a pretty good coefficient of variation. I mean, it's a little high, right? Remember the coefficient of variation? Your standard deviation over your average. It's a little high, but that's okay. It's believable. 200 over 1,000, so 20%. That's okay. It's not the 10% that we strive for, but it's okay. So the other thing that's cool about this problem is that it actually says, okay, well, what if we have we have 1,000 light bulbs or 2,000 light bulbs, and it's a cool question. How many do you think are going to fail after 700 hours? I know the average is 1,000 hours. Put your units in there so that I know what's going on, right? This is 2,000 bulbs, 1,000 hours, standard deviation. I already know it's hours, so I don't have to write that there. And the question is asking me, how many lamps are expected to fail in the first 700? So if the average is 1,000, and again, people get this wrong all the time. Don't put it up here, right? The 700 is down here. Right? I want to know this area. The question is asking me, what is the probability, or more specifically, what is the number? But first I have to figure out the probability. What percentage of light bulbs are going to fail? And again, when you make the drawing, you realize you don't have to do the subtraction of 1. This is going to be a little bit easier. I don't have to subtract 1 because this is what my chart's going to give me. So, you know, your method to your madness here, again, let's calculate a z-score, or you could just use Excel, I guess, at this point. Let's just use Excel because it's, why not, right? So when you do use Excel, you know, make sure you tell me what you're, you know, what are you going to input? Well, let's input, well, normal distribution. Again, you could just submit to me the Excel file, I suppose. As long as the formula's in there, I'd be okay with it. What would I put in here though? So I'm gonna want here 700, 1,000, 200, and cumulative. And this should give me that probability. So this, again, write down what you're calculating so that I don't think you're just getting lucky. Try again, in any sort of math or scientific process, unless you're working for a company that wants you to keep your process secret, and that means you have a very good job, you want to write down exactly how you're achieving your results. If you're in academics, right? Academics, you have to. That's the idea of academia. Okay, so this should give me, yeah, that's the right number. So 0.06681. That's the well, the percentage would be 6.7% approximately, right? So 6.681% of light bulbs should fail. So all you'd have to do here to figure out how many out of 1,000 would fail, right? The number of failures. The number of expected failures in this case. I always take marks off for you guys for formatting, so I better get it right myself. Number of expected failures in this case, I would say is, well, 2,000, which is the number of light bulbs, times this one. And because it's a discrete data set, let's get rid of the decimals, right? It's a continuous so this is a little bit confusing. It's a continuous probability function because time and the light bulb time is a continuous function, right? Hours and time is, when you're measuring it, is always continuous, but the final answer is discrete. Right? The number of light bulbs, which is the final answer, is a discrete value. So that's a really awesome question for that reason as well. I need to get rid of the decimals, and you always round up with when you're going this way. Like if it said 3.6 people, you would say 4. We would expect, you can't get 0.6 of a light bulb, so you would say that many light bulbs. That many lamps would fail. So we'll talk more about, you know, having a conclusion after the midterm when we start getting into chapter 7 and chapter 8, where you do have to have a conclusion. But it's good practice to say, you know, 134 light bulbs are expected to fail. That's good practice to make a clear answer. because that's the kind of stuff your manager's going to want to hear, right? Your business leader, they're going to want to know, you know, they don't want to see all this. They want to hear this, right? This is the money statement, right? The conclusion is the one that you're going to be presenting to your shareholders, or the ones that you'll be presenting to your you know, your manager, the money person. There's always somebody with more money than you that you're going to try and explain technical concepts to. And that concluding statement is what you're going to tell them. You know, you're the nerd that's doing all the calculations, but you have to walk into a boardroom at some point of your job and say, we're going to need 134 more light bulbs.